All right, welcome back. This time we're going to talk about ensemble methods. But before we get started, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. So, ensemble methods, bagging and boosting. Ensemble methods combine predictions from multiple base models to produce stronger overall performance than any single model. In AWS, ensemble techniques, particularly boosting through XGBoost, play a central role in supervised learning workflows involving structured tabular data. Rather than relying on one decision tree or regression model, ensemble learning aggregates results from many models. Amazon's product recommendation engine exemplifies this approach, combining collaborative filtering, content-based filters, and boosted decision trees to deliver accurate predictions. So, understanding bagging. Bagging, or bootstrap aggregation, trains multiple models independently on different random subsets of data sampled with replacement. Each model votes on predictions, and the final result comes from aggregating these votes through majority voting for classification or averaging for regression. Bagging trains models in parallel, reduces variance, and improves robustness against overfitting. Random forest is the most famous bagging implementation, particularly effective for tabular classification tasks with noisy data or overfitting risk. In AWS, SageMaker's built-in random forest algorithm implements bagging. You upload tabular data via S3, configure a training job to run multiple trees across training splits, and SageMaker handles the parallel execution automatically. So, understanding boosting. Boosting trains models sequentially. Each new model attempts to correct mistakes from previous models by adjusting weights on incorrectly predicted observations. This sequential refinement reduces bias and achieves high accuracy, making boosting the technique of choice for competitive machine learning. XGBoost, or extreme gradient boosting, is the most popular boosting algorithm, dominating Kaggle competitions and powering production systems for predictive maintenance, churn prediction, and fraud detection. SageMaker provides a highly optimized distributed XGBoost implementation through pre-built containers accepting CSV or libs SVM format data from S3. So how do you compare the approaches? All right. So bagging and boosting differ fundamentally in execution and goals. Bagging trains in parallel, aiming to reduce variance and prevent overfitting. Boosting trains sequentially, targeting bias reduction and accuracy improvement. Bagging executes faster with parallel resources, while boosting's serial computation takes longer. Bagging is less likely to overfit, while boosting can overfit without proper regularization. Random forest exemplifies bagging in SageMaker. XGBoost represents boosting. So why does AWS emphasize ensembles? Ensemble methods deliver high accuracy on complex classification and regression problems involving structured data. Managed services like SageMaker scale ensembles easily without infrastructure management. The platform supports both built-in algorithms and custom container-based training, providing flexibility for specialized ensemble implementations. So how you would do this would be in the SageMaker, create the training job, and the notebook. So we're not going to go do that. It's just going to take too much time. You'd adjust your parameters, make sure your compute is up to date, usually using a GPU base, so an ML.P, but you can go for CPU. An ML.M would be suitable. Then you'd launch it, monitor it in CloudWatch or in the SageMaker console. So costs, let's talk about that one. SageMaker trains costing based on instance type and duration. So an ML.M or ML.C instance will cost approximately 17 to 25% per hour. XGBoost itself adds no additional charges beyond instance costs. S3 storage runs about 2 cents per gigabyte per month on standard tier. Real-time endpoints will bill per hour of uptime that you can configure auto-scaling to minimize costs during low traffic periods. And you can always reduce expenses by using spot training with checkpoints, which can cut costs by about 50 to 90% for interruptible workloads. So you can leverage that batch transformation instead of real-time endpoints when immediate responses aren't required. And batch processing costs will significantly decrease more than persistent infrastructure. So for the exam, remember this. When questions ask about improving model accuracy, handling structured data, or choosing between parallel and sequential ensemble approaches, understanding bagging and boosting and their SageMaker implementations will guide you to the correct answer. Anyways, that's all for this time. Thank you for joining. But before you go, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you. Have a good day.